Hello everybody, welcome to another physics video. Today we're going to go more into rotational motion, a little more in depth. As always, thanks to Krish Kotak at the University of Utah for providing the problems for this video. I'll let you pause the video and read this briefing for the setup, for the context for the problems we're going to be solving today, and then we'll go ahead and get started. So to start things off, we have our satellite and we want to keep it in an orbit of 500 kilometers above the Earth's surface, as stated here. And then we're given a few important values. And the problem is to determine the orbital velocity that the satellite must maintain for a stable circular orbit at this altitude. So we'll first draw our free body diagram. We'll say that this is the Earth. Here's our satellite. The only force acting on this satellite is going to be the force of gravity. And again, that force of gravity will always point inwards no matter where we are in orbit. This is the only force, and it is a centripetal force. So we can say that the force of gravity is equal to the centripetal force. The equation for gravitational force is given by gravitational constant g times the mass of one object, so in this case the mass of the Earth, times the mass of the second object, which we'll just say little m, divided by the radius squared. And then since this is equal to the centripetal force, we can say that this is equal to the mass of the satellite times v squared over r, which comes from centripetal acceleration equals v squared over r, and so mac and mv squared over r is equal to centripetal force. Right away, we can cancel the two little masses, and we can cancel one of our radius. And then finally, we take the square root of both sides, and we're left with v is equal to the square root of g, the mass of Earth, divided by the radius. The radius in this case, we have the Earth's radius is 6.37 times 10 to the 6th, and we know that the orbital altitude is 500 kilometers. So our total radius is going to be 6.87 times 10 to the 6th. We can plug this value and our value for the mass of the Earth here and our gravitational constant here into our equation for velocity, and we get that velocity is roughly equal to 7,613 meters per second. You don't need to do any unit conversions here because this is in meters down here, the mass of the Earth is in kilograms, and the gravitational constant is also in those SI units. For this next problem, we have two main solar arrays that must be unfolded from stowed position. Important information, we have that the mass is equal to 15 kilograms for each panel, and the length is equal to 4 meters, hinged at one end. The motor applies a sustained net torque of 0.8 Newton meters during the initial phase. And then all of that is summed up for us here. The first question is to calculate the moment of inertia of a single solar panel about its hinge axis. Important, we can model the solar panel as a uniform, rigid, rectangular plate hinged at one end. That's important for the moment of inertia. So I'm just going to draw kind of what's happening here. There's a box of some sort, and then there's a hinge here with a solar panel coming up out of it. And that solar panel starts down here, and we want it to end over here. So overall, it's going to go 180 degrees. Then there's another one doing the same thing over here. So, since we know that it is a uniform, rigid, rectangular plate hinged at one end, you can look up either in your textbook or online the moment of inertia of an object at this is 1/3 the mass of the object times the length of the object squared. So in this case, this is 1/3 times 15 kilograms, located here, times 4 squared. And if you calculate this out, this is equal to 80 kilogram meters squared. Question 2 asks us to determine the resulting angular acceleration of the panel upon initial motor engagement. The equation we want to use for this is we know that the net torque is equal to the moment of inertia times the net angular acceleration, or our alpha. So we can rearrange this to solve for our alpha, since we know our net torque and we know our moment of inertia I. We know that alpha will equal I over torque. Plugging in our values, we have alpha is equal to 80 divided by, I did my algebra a little wrong there. We're solving for alpha. So we divide out the moment of inertia so that alpha is equal to the torque over I. So in this case, it's 0.8 divided by 80. If you plug that into the calculator, you get that alpha is equal to 0.010, and then this is going to be radians per second squared, since it is an angular acceleration. Finally, we know that the panel must deploy 180 degrees to lock into position. Assuming our constant angular acceleration, calculate the total time required for the panel to fully deploy from rest. In this case, we can use our equation theta is equal to omega naught t plus 1/2 alpha t squared. Assuming that it's deploying from rest, which it says here, omega naught is 0, so this whole term goes to 0. So theta is just equal to 1/2 alpha t squared. We know theta, we want our final theta to be 180 degrees. We calculated alpha earlier, so we can rearrange this to solve for t. You get that t is going to be equal to the square root of 2 theta divided by alpha. So t equals the square root of 2 times 180 divided by alpha, where our alpha is 0.01. If you plug this into the calculator, you get that our time for the full deployment is roughly equal to 25.1 seconds. For our next problem, we have that the central module, which has a total moment of inertia of 15.5 kilogram meters squared, is fully deployed. And then we have a 1.5 Newton thruster that fires 0.05 meters off the satellite's center of gravity. Let's draw this out down here. So we'll say that here is our overall satellite, and then here are the arrays. So they're fully deployed now. Say that this is the line for the center of gravity, assuming that it's a uniform object. And then right here, there is a 1.5 Newton force applied. And then the distance here is 0.05 meters from the center of gravity. The first question wants us to explain exactly how firing a linear force away from the center of gravity on a rigid body induces rotational motion, and how this is defined mathematically as torque. we know that torque, the equation for it, is given by r, which is the distance from the center of gravity, times the force that is applied, times sine of theta, where theta is the angle between the applied force and the moment arm. So in this case, this is a 90-degree angle, and sine of 90 degrees is just 1. So our torque is just going to equal R times F. Torque works in the same way that a regular force does. It's defined as the moment of inertia times the angular acceleration, and a force applied in some linear or two-dimensional direction or three-dimensional direction is the mass times the acceleration. So you can kind of think of it as I is similar to the mass, and angular acceleration alpha is similar to acceleration. So we have torque over here and forces over here. And torque works the exact same way, but it works in a rotational direction. So it causes something to rotate about its center of axis, whereas a force would just cause it to move in space. Question 2 wants us to calculate the magnitude of this unwanted torque created by the thruster anomaly. We already have this equation we found earlier. So we know that torque is going to equal 0.05, which is the distance from the center, times 1.5. And then this is the force. If you plug this into the calculator, you get that our torque is 0.075 Newton meters. Question 3 asks us to determine the unwanted angular acceleration of the central module due to this misfire. We can recall that torque is equal to the moment of inertia I times alpha, and alpha is what we're solving for. We know torque, it's 0.075 Newton meters, and we're given our moment of inertia up here as 15.5, so we can rearrange this to say that alpha is equal to torque divided by moment of inertia, just like we did earlier. So in this case, alpha is 0.075 divided by 15.5. If you plug this into the calculator, you'll find that alpha is roughly equal to 0.0048 radians per second squared. For this last problem, we have a high-speed internal gyroscope that counteracts the spin from the earlier force. The wheel is modeled as a solid cylinder with radius r equals 0.25 meters. In order to generate the appropriate counterspin, the wheel must reach a required rim speed of 12.5 meters per second. The first question says that the relationship between the rim speed of the spinning wheel and the angular speed is the same as the condition for rolling without slipping. And it wants us to state the equation. I'll just go ahead and state it. The condition for this, zoom in, is that the speed of the rim is equal exactly to the radius times the angular acceleration. The angular velocity, omega. Question 2 wants us to calculate this required angular velocity to achieve the specified 12.5 meters per second rim speed. So we know that our rim speed, v rim, is 12.5. Well, let's actually solve symbolically first, even though this is a pretty simple equation. So we want our angular velocity. We have our speed, and we have our radius given here. So we can divide both sides by r. We get v over r is equal to angular velocity. Now we can plug things in. Our speed is 12.5 meters per second, and our radius is 0.25 meters. So we get that 12.5 divided by 0.25 meters is equal to our angular speed, which if you plug this into the calculator is equal to 50, and then this will be in radians per second since it's angular speed. The next question asks us to calculate the average angular acceleration applied by the motor during this crucial counterspin phase. Angular acceleration is given by the change in the angular speed over the change in time. You may realize, or you may make the connection on your own, that this is pretty much the same as just saying d omega dt, if you know a little bit about calculus, which makes a lot of sense because angular acceleration is the derivative of angular velocity. So our delta omega, or our change in angular velocity, is going to be our 50 radians per second. And this is just from rest to the necessary speed. How much speed do we gain? Which is 50. So we'll say alpha is equal to 50. And then our change in time is 2.5 seconds, given here. If you plug this into the calculator, you get that our average angular acceleration is equal to exactly 20 radians per second squared. Our last question says, given a mass of 2 kilograms, calculate the average torque required to achieve the average angular acceleration. So we know that torque average will equal our moment of inertia I times our average angular acceleration. We don't know moment of inertia, but we do know the mass. And we also know, if you read the question carefully, we know that the reaction wheel is modeled as a solid cylinder. So if you look up the equation for the moment of inertia of a solid cylinder, you get that it is equal to 1/2 the mass of the cylinder times the radius squared. In our case, this is 1/2 times 2 times the radius, which is 0.25 meters squared. The 2's cancel out, and we get that 0.25 squared equals our I, and this is equal to 0.0625. Now, we can plug this into our equation and our earlier calculated alpha value to find the torque, or the average torque, is equal to 0.0625 times 20. Plugging that into the calculator, we know that our average torque is about equal to 1.25 Newton meters. One last thing, and then that's the end of this video, is it may be confusing to think about things in terms of average torque versus overall torque versus torque at a specific moment. The key thing to realize here is that the average torque is going to be the moment of inertia times the average angular acceleration. Moment of inertia isn't an average value, it's an inherent value based on mass and radius, so it doesn't need a little subscript there. So if we're using the average angular acceleration, that gives us the average torque. Whereas if you were to use the angular acceleration at a specific moment in time, it would give you the torque at that specific moment in time. But I hope that clears things up, and I hope that this video is helpful for any tests or exams you have coming up. And as always, I wish you the best of luck.